So, very interesting. I wanted to draw a little snake for you just to have cute representation. Here's a snake, right? Okay, let's do it. The snake. We have snakes in Arizona for you to know. So just like be careful when you hike. That's why in Arizona, that's what I told. Many people use the stick when they hike, not just because it's fancy and helps you. When you kick it on the floor, it makes vibration and scares away snakes and scorpions. Apparently, it kind of actually saves your life. Who knew? So here's the snake. So the idea is I put some segments or pencils on top of the snake. And actually, I can just make a photo of the snake, so I don't have to approach it. And then do it on the photo if it's 1-to-1 ratio, right? So I put some pencils like so. And then I just collect those pencils and see how many pencils I used to put it on a snake. And then the smaller the pencils are, the more accurate the calculation of the lengths. That's it. Very simple idea. Now, the formula comes in right now. And that's going to be your job to memorize the formula. Formula number 1, arc lengths. So let's call it arc lengths or the lengths of the curve. They kind of did not agree in English how to call it. Formula number 1 will be L is definitely very classical notation for arc lengths, L, because it's lengths. From A to B, a huge square root, 1 plus derivative. Derivative with respect to y, dy dx, square it, dx. It comes from Pythagorean theorem, and you can check the derivation of 1 plus derivative squared, but the idea is always 1 plus derivative squared. Or if you choose to use dy case, and you will see in the examples why would you do that, c to d, a huge square root, 1 plus dx over dy. That's derivative of x now, squared dx. Two main formulas for this chapter, like so. The idea is the same though for you to know. It's integral a square root 1 plus derivative squared. That's how I remembered. 1 plus derivative, go away, squared from a to b dx. So I remember just the general shape of it. 1 plus derivative squared. And then what kind of derivative depends on the x or dy case. That's how I remember it. Yes? Yes, let me see. dy, thank you. Testing, good job, thank you. dy. Good job. So this is case 1 versus case 2. For the first case, y will be depending on x. It's a function on x, and it is on interval a and b. For the second case, x depends on y. So x is dependent variable, and then it's happening on c to d, like so. Two cases, case 1, case 2. Then I will tell you one more formula. We'll be using it for the exam 3, at the very end actually, exam 4, which is final exam. This formula is using parameterization, which will be super fun topic to explain in the months. Integral from a to b, a huge square root. And then derivative of x with respect to t, a third variable called parameter, plus derivative of y with respect to t, both are squared, dt. That will come in the future. We're going to teach you parameterization, which very naturally takes you to calculus 3, which introduces more variables. That's why it's called multivariable calculus. T, t, and t. And then in calculus 3, we're going to teach you more formulas, because it makes sense to take the line we just saw, so something like a kite. So we're going to ask you on the exam, find the length of the kite. Do you know what kite is, right? It's like this. Okay, how does it look? It's like, oh, the triangle, yeah? Usually it's a triangle flying around. So find the length of the kite. That's exactly arc length. But if it goes to 3D, then it kind of becomes a 3D object. And we're going to teach you one more formula in calculus 3 for 3D cases. Pretty cool idea. But in general, the whole idea of the curve is 2D object, even if it's floating in 3D. It's flat, it's convenient, it's nice to work with. Anyway, I'm talking too much. If I show you the example, you will see how straightforward it is. There's nothing to complicate in this chapter. This is a student's favorite chapter because finally it's not hard. Not too hard. Find the arc lengths of. Find the arc lengths of y equals 1 plus 6x to the 3/2. I think this is example from the exam. So just letting you know, it looks very familiar, I see. From 0 to 5. Very classical example. Usually it's multiple choice case on a test because we're just testing your knowledge of the formula. So, you see, I don't give you if it's A or B, but kind of you can guess. Y equals 1 plus 6x to the 3/2. So 0 and 5 are A, B, or C and D. A and B. So it immediately gives you case 1. Like if everything is given in terms of x, why would you go to case 2 then? Solution. We can see it kind of follows us or leads us to use case 1. Formula for case 1 is L equals integral from A to B, a huge square root, 1 plus derivative squared dx. And now you just need to figure out that you are differentiating the function of x. So you don't even have to do anything extra. You just find derivative of the given function, plug it in, square it, add 1, take square root, integrate. That. Either do it separately or do it right away. I'll do it separately for this case, but the formula is ready. This is the formula. So f of x prime is derivative of the given function 1 plus 6x 3/2 prime. Derivative of 1 is 0. Derivative of 6x 3/2 is 9 square root of x. Exactly. Thank you. Plug this into the integral. Don't forget to square it. That's very important. People who forget to square it usually have trouble to integrate. Integral becomes easier in most of the examples. L equals integral from A to B. Can you tell me A and B? 0 to 5. Huge square root. 1 plus 9x to the 1/2. Don't forget to square dx. This is the most important part. After this, we're going back to the techniques of integration, and we just ask you, do you remember how to integrate stuff like this? But when we use techniques of integration, now we just teach you how to actually use integrals for real-life applications. What is the length of the sound wave? What is the length of the ocean wave? And your hair, and your leg, all those kind of things. That's literally arc length. Questions about how did I create it? A huge square root, 1 plus derivative squared. If you say it out loud, it's easy to remember. If you don't square it, it's actually harder to integrate. But since I'm squaring, the square root goes away. So it is just 1 plus 81x. Too fast, or you agree? People who just blinked or using their smartphones, did you notice 81x? Who can integrate this? 1 plus 81x in the square root. Looks impossible. What do you think? I don't think we can we? Yes? You can. It's just use up, exactly. Thank you. Always question when someone says it's impossible. This is use up. Do you want to do the whole use up or shortcut? There's a shortcut if you don't remember. I will show you the shortcut, but you can perform use up while I'm showing you the shortcut. The shortcut says if you have an integral a x plus b to the n, just make sure n is not minus 1. Then the use up shortcut says just use power rule. It is power rule. So n plus 1 over n plus 1. Undoing chain rule tells you to do what? Divide by the leading coefficient. That's a use up shortcut. Divide by the leading coefficient. The only exception is 1 over x. That's logarithmic function. So n should not be minus 1. But otherwise, it's actually U sub shortcut for the power rule. No, U sub shortcut for the U substitution that works on the power rule. U sub shortcut. So now using that, who can tell me the answer? Square root of 1 plus 81x. Anyone over there? Do people even see me over there? Over there? Who wants to tell me? Just use the formula. Anyone? I should start either giving extra credit for answers or taking points off if you don't answer. Or calling by names. In Zoom, I used to call by names. It was very convenient. Yes? 1 over, let's see, 1 over 81. Oh, you see, you're already figuring out the coefficient. Over here, like so. Square root of 1 plus 81x. That is very confusing. How did you get this? But, like, good job. Yeah, I remember that you have very good mind calculations of stuff in your mind. Who can explain how did we get it? It is correct. Let me not skip this step so people have good notes. 1 plus 81x used to be raised to 1/2. Formula says what? Add 1. 1/2 plus 1 is what? 3/2. Dividing by 3/2. And then what's missing? 1 over 81, because it's dividing by the leading coefficient, which is a. Then don't forget, it's not plus c. It's from 0 to 5. Thank you, both of you. Very good. And now you simplify, and it's going to be 2/3 divided by 81, blah, blah, blah. I actually have a simplified version. We're almost done, I promise. We're almost there. 10 minutes left. Oh, 5 minutes left. So if you simplify, it's going to be 2 over 243, 406 to the 3/2 minus 1. This is the exact answer. It's better be positive, because what are we looking for here for? Area. Arc lengths. Yes, thank you. Arc lengths, which is technically speaking area with the 0 width, right? So you're not wrong here. It is a good point to mention that it is a physical object. It's not supposed to be negative. It's the length of the rope. So if you find the length of the rope, it better be positive. And it's the area with 0 width. That's why it looks kind of what we did before. It's still integration, but we're using distance formula here. The distance formula, you see, square plus square, derivative squares. Derivatives because we have little changes. The change is coming from the slope, right? If you can see, it actually is a secant line. Secant line has connection with a slope. It's all coming from Pythagorean theorem and the right triangle, blah, blah, blah. And that's why derivative is involved. And then you use this formula to have different cases, dy case or dx case. There's nothing extraordinary in this chapter. It's basically working on this formula again and again. So technically speaking, I'm done with the whole chapter in 20 minutes. It's very simple. So we're going to move on next on Wednesday to the next chapter.